Good. So welcome. My name is Jairo Sinova. Together with Karin Eversosite and Martina Schliemann, Burkhard Hillebrands, and Amadeus Chloe, we're putting together this joint effort between the Spin Phenomena Interdisciplinary Center, SPICE, which many of you may have visited already, and the Collaborative Research Center, SPIN+X, between Mainz and Kaiserslautern. In this time where we are all isolated and we found ourselves not traveling anymore to the conference and seeing each other directly, which is still quite important to do, to share some of the sciences that we have. I'm going to keep this quite short. The talks will be on Zoom, and then we have here so far room for 500 people, but it's also live streamed in SPICE YouTube right now, which we have about 200 now watching at this very moment. You can go directly to the links on the SPICE YouTube. The talks typically are on Wednesday at 3 p.m. Central European time, such that they're accessible to the US as well as to Europe, and hopefully in the evening, unfortunately, in the Asia. This format is a webinar format, meaning that when you come into the room, you will not be able to talk or chat with each other, but you will be able to ask questions. So if you send a question or write a question, I will be able to see it and I will monitor it during the talk for possible questions for Professor Jungwirth. And this is, of course, complementary to these online spintronics seminars that are started by Kirill Belashenko and Yafang and the University of Denver, Nebraska. And you can see many of the talks that they're also doing as well at a slightly evening time here in Europe, but also very good talks that I can recommend. And just so you know, we have a lineup of different speakers that we hopefully will do every week. So far, we're only thinking once per week because otherwise it will be too crowded in the amount of talks that we will have. And this week, we have Thomas Jungwirth, and next week, with a topic that is more in topological end, we have Carlo Benacker from Leiden University, which we're looking forward to. So with this, I would like to introduce the speaker today, Thomas Jungwirth. He's the head of the Department of Spintronics and Electronics at the Institute of Physics of the Czech Academy of Sciences, and as well as a professor at the University of Nottingham. Graduated in 1997 and was a postdoc in Indiana University and the University of Texas for about 5 years afterwards, before he came back to the Czech Republic to lead that department with Alan MacDonald, and where we also overlap and have ever since had a long career collaboration. He's gained many, many awards. The Academy of Science of the Czech Republic. He's also got an advanced grant, but also is a member of the Scientific Council of the European Research Council. Has many publications, 5 reviews of modern physics, which is more than anybody would like to do in a lifetime, and large impact in our field. And has begun, or really one of the starters of the field of antiferromagnetic spintronics as we know it, in manipulating directly antiferromagnets, having organized here with us SPICE workshops on antiferromagnetic spintronics. And with that, I think that is enough of the introduction. So I'm going to myself stop sharing, and I will ask Thomas to please go ahead and actually I should 1 second for a second record. And then please go ahead and Thomas, start your talk when you want to share. Okay, we'll see you talk. And I will mute myself now.
Okay, good afternoon, everybody. Thanks, Jairo, a lot for putting this series of seminars together, online seminars, and of course, the rest of the Mainz and Kaiserslautern crew for setting this up. So good afternoon, everybody in Europe, and good morning if there's anybody watching or listening from the States, and I guess for people in Asia, I should just wish you good night for the moment. So I was asked to give an overview talk on antiferromagnetic spintronics, but the field is now becoming very large, so there's definitely no chance that I can cover all the new developments in the field. This is just a reminder of a few review articles. There's several articles that are appearing virtually every year. So this is just a quick look at a collection of review articles that we published in 2018. And it just shows that there are many different areas of antiferromagnetic spintronics. And I'm also using this slide to acknowledge at least some of the key contributors, key people that have contributed to the field over the past few years. Now, one of the very active areas of research in antiferromagnets already for quite some time and certainly still very active is research in insulating antiferromagnets. And there are many new exciting studies on ultra-fast optical or terahertz control of spins in antiferromagnets, long-distance magnon transport in antiferromagnetic insulators. And antiferromagnetic insulators can also host more than one order. The spin order or magnetic order can be complemented with the charge order in multiferroic materials. So this is a very active research area, but I'm not going to cover this area at all in this talk. What I'm going to focus on is spintronics in its original sense. That means spin electronics in conducting materials, and in our case, these are conducting antiferromagnets. Also, for this part of spintronics, the spintronics in conducting antiferromagnets, there is a recent review that's been just posted quite recently on the archives. So then let me start. When we talk about spin electronics, I divided the talk basically into two sections. One is a section on readout in spintronic devices, and it will follow with a section on writing. And I will also make a few remarks towards the end about retention or relaxation of the recorded signal. So let me start with readout. And I need to first compare antiferromagnets with a much more mature, obviously, field of ferromagnetic spintronics. So just a reminder, in ferromagnets, the readout mechanism that has been introduced first was anisotropic magnetoresistance. So this is the effect in which you take a simple ferromagnetic resistor, and its resistance depends on the angle of the magnetization in this resistor, for example, with respect to the direction of the probing electrical current. So these devices, these anisotropic magnetoresistance devices, were first introduced as readout elements for magnetic stripes, tapes, and eventually hard drives. But also people realized in the 80s that you can completely forget about the magnetic medium, the disk, for example, and use the AMR element itself to also store the information and then make integrated circuits of these elements and create solid state magnetic random access memory. And there have been some prototype devices based on anisotropic magnetoresistance readout. But we all know that the real breakthrough in spintronics was due to the discovery of giant or tunneling magnetoresistance effects. They are the resistance changes, the relative changes are 1 or 2 orders of magnitude larger than in anisotropic magnetoresistance. And instead of using a simple magnetic film device, these devices comprise at least of 2 magnetic parts. One is the reference, which is a fixed magnet, and then we have the recording element, and then depending on the relative orientation between the reference and recording magnet, we have either low or high resistance. In this context, I'd like to emphasize that so far there is no successful realization of these GMR or TMR multi-layer structures in antiferromagnets. Obviously, when you think of antiferromagnetic moments, it's clear that realizing these type of devices is much more complicated than in ferromagnets. And indeed, in the entire talk, I will then focus on devices which are just made of simple single-layer antiferromagnetic films. So here is an example of the transmission electron microscopy image of a single crystalline epitaxial film of copper manganese arsenide, which is a collinear antiferromagnet, a workhorse material for many of the studies of metallic antiferromagnetic spintronic devices. So when we talk about readout through resistivity in a simple film, resistivity or conductivity, let's take a look at this transport coefficient from the very general perspective. So when we have conductivity, we can divide it, the tensor, into the symmetric part and the anti-symmetric part with respect to the indices, where the indices correspond to the direction of the electrical current and the applied electric field. Now, if we combine this with Onsager relations, we see that the anti-symmetric component is going to be odd on the time or spin reversal, while the symmetric component of the conductivity tensor is going to be even on the time reversal. Now, when we look at this odd on the time reversal component, the so-called Hall component, because of the property that is odd on the time reversal, it vanishes in systems which have time reversal symmetry. Now, if we take a look at this very simple model of an antiferromagnet, a linear antiferromagnet, we see that if we do the time reversal operation here, we flip all the spins, the crystal looks different. So the crystal does not have a time reversal symmetry. However, if we add to the time reversal another simple symmetry operation, which is, for example, translation or inversion around this inversion center, we see that we recover the original state. And linear response conductivity is invariant under these operations of simple translation or inversion. So it doesn't matter if you do it or not. And from this perspective, such a simple model antiferromagnet behaves as if it had time reversal symmetry. So, so for the linear response coefficient in such a model, the anomalous Hall effect would vanish. Now, when I look at our workhorse collinear antiferromagnet copper manganese arsenide, it has exactly this symmetry property. It has the combined PET symmetry, so anomalous Hall effect is not present in the system. So we can only work with the symmetric tensor components of the conductivity or resistivity, but that's okay, because anisotropic magnetoresistance, the fact that it's been used in ferromagnets for many, many decades to sense the changes in magnetic order, it is part of this symmetric or the ordinary conductivity components of the conductivity tensor. So anisotropic magnetoresistance can exist in any system, including these PT symmetric antiferromagnets, and in principle in any antiferromagnetic system. So we can detect then, for example, the reorientation of the magnetic order from a direction orthogonal to the probing current to the direction parallel to the probing current, and what we will see is a change in the resistivity of the material. And these are real experimental data where we see that we reorient the nail vector or the antiferromagnetic moments by 90 degrees, and we see these changes in the resistivity or resistance signal due to anisotropic magnetoresistance. What I'd like to emphasize here is, and this is generic to the resistivity signals that we can detect in thin films, that they tend to be relatively weak. That was the reason why in ferromagnets, people switched eventually to these multi-layer TMR or GMR effects. So again, also in antiferromagnets are no exception. We work with simple films, and the resistivity change due to AMR we see is of the order of fraction or maximum of the order of percent. What is nice, however, about this effect that it has optical counterparts. The optical counterpart, either using light or X-rays, is called a magnetic linear diachroism. And in particular, if we use X-rays, short wavelength X-rays, we can do microscopy. So besides the electrical signal, which probes the average change over the entire electronic device, in this microscopy, we can zoom in and look at individual domains. So these are micron-sized domains. And what you see in this movie is switching between the two orthogonal direction of this several micron size domain in copper manganese arsenide. Now, we had electrical version of the anisotropic magnetoresistance. We have the optical counterpart, or linear diachroism, but you can also have thermoelectric counterpart, which is called the magneto-Seebeck effect. So now instead of applying electrical bias, you can apply thermal gradient, and in response, you will measure electrical voltage, and now this electrical voltage will depend on the orientation of the spins or the Nail vector. The nice thing about this probe is that you can use focused laser beams to induce local heating and then measure the electrical thermal voltage response to that. So you can use it instead of going to synchrotron for your X-ray imaging. You can do experiments in the lab with the focused lasers, and you can also image these antiferromagnetic domains. So here's an example of a recent work where side by side on exactly the same piece of material, you see the antiferromagnetic domains in copper manganese arsenide imaged in lab by the thermal imaging, or at synchrotron by the X-ray magnetic linear diachroism. Now, I mentioned already that one of the issues working with thin films are the weak electrical readout signals. So one way how to possibly get around this problem is to find singularities, if you want, in the topology of electronic structure of these materials. And then due to this singular feature, one might also expect to find a singular behavior of response, electrical response, including the anisotropic magnetoresistance. And here, as an illustration of this principle, I'd like to emphasize that the PT symmetry, this was the symmetry that did not allow for the anomalous Hall effect. It, in fact, allows for having a topological Dirac point in the electronic structure. Because if you have the combined PT symmetry, it guarantees that you will have a Kramer spin degeneracy of your bands. And if two such spin degenerate bands cross, you will get this topological Dirac point. We are familiar with this Dirac points from graphene, and I'd like to emphasize that in graphene, the Kramer's degeneracy is because there is both individual parity symmetry and the Timer-Rosso symmetry. That is not present in this antiferromagnet. It only has the combined symmetry, but that's enough for having the Kramer's degeneracy. I'd like also to make a remark that this is only possible in antiferromagnets, while in ferromagnets, you cannot have systems which would have this combined PT symmetry. So the Dirac points are in principle only allowed in antiferromagnets. Another side remark here is that if we look at all possible symmetry groups of magnets, there are 122, and all of them can host antiferromagnetic order, including those with the PT symmetry, while ferromagnets are only a subset of 31 of this magnetic point group. So that already tells you that if you're looking for some special symmetry, and by symmetry allowed some special topology in the band structure, antiferromagnets will give you much broader playground. But how can we use it for some magnetoelectric response? So what can happen is that this Dirac point is protected, so there is no hybridization, and we have a true crossing of the two doubly degenerate bands only for the nail vector orientation or direction along some special high symmetry crystal axes. Once we change the orientation of the nail vector, this protection of the Dirac crossing is lifted, and we can open a gap. So by just changing the direction of the magnetic moments, we can change the system from a metallic, semi-metallic system into an insulator. And this is due to the reorientation of the magnetic moment. So we have this metal insulator transition and accompanying huge, in principally huge singular anisotropic magnetoresistance. But an important caveat to make here is that for this to happen, you have to have these Dirac points, these topological features, to be at or very close Fermi level, and no other trivial bands crossing the Fermi level. Now, if we look at our workhorse tetragonal copper manganese arsenide, it has these Dirac crossings, and you can close and open the gap by changing the direction of the nail vector. But what you see is that these features are buried deep in the Fermi sea, so they are not going to affect strongly our magnetotransport property. There's a theoretical prediction, which is yet to be verified experimentally, that there are other antiferromagnetic systems which might have the Dirac point right at the Fermi level and no other bands crossing. And an example could be orthorhombic phase of copper manganese arsenide. Well, let me get back to the general expression of the conductivity tensor here and go back to the Hall effects. Maybe we were too fast in discarding Hall effect in antiferromagnets. In the simple model, and certainly in those PT symmetric antiferromagnets, Hall effect is prohibited. However, if you look at other realizations of antiferromagnetic phases, like for example, in this case of this non-collinear systems where you have 3 different sublattices, altogether the net moment vanishes, but for such an arrangement, not only the time reversal, but also all the other combination of time reversal plus translation or time reversal plus inversion symmetry operations, they are broken. So this means that in principle, these systems can allow for anomalous Hall effect, something that has been identified or realized about 5 years ago. And what it means is that these systems can have anomalous Hall effect. Now, here is an example of the experimental demonstration of anomalous Hall effect in this non-collinear antiferromagnet manganese free tin. But what I'd like to emphasize again is that the signal, again, we're in simple magnetic films, the signal is relatively weak. The relative size of the Hall resistivity that you measure relative to the longitudinal resistivity is again of the order of 1%. Compared to ferromagnets like iron, for example, this is a similar value. It's just the problem of simple films generating these relatively weak magnetotransport responses. And again, one way how to look for singular effects, much larger amplitudes, is to try to work with some topological features in the electronic structure. In these broken PT symmetry systems, you cannot have the Dirac points, but the Dirac points could split into 2 doubly degenerate crossings, which are called the wild points. And again, if you manage to have these wild points close to the Fermi level and no other trivial bands, this can have some singular effects on the corresponding magnetotransport. Again, unfortunately, this doesn't seem to be the case of manganese free tin. It is a wild antiferromagnet. It does have these crossings, but they're not the only ones that contribute to the anomalous Hall effect. There are also trivial bands that contribute. And similar to anisotropic magnetoresistance, I'd like to emphasize that you can have the optical counterparts of the Hall effect, which is called the magnetic circle diaprism. And you can also have the thermoelectric counterpart, which is called the thermoelectric spontaneous or anomalous Nernst effect. So here we have an example of a recent study which used the anomalous Nernst effect in combination with the focused laser spot local heating, again, to generate an image of domains in this non-collinear antiferromagnet manganese free tin. Now, in particular, when we want to search for materials which would have this singular behavior due to the special topology, we need to really scan through various materials, because it's, in the end, is the chemistry and the specific crystal structure which will determine whether the Dirac points or the wild points are close to the Fermi level and no other bands crossing the Fermi level. So you would like to have as broad as possible playground of materials where you can search for these phenomena. Unfortunately, there is not that many non-collinear antiferromagnets. However, there is a large family of collinear antiferromagnets. So it would be really very nice to have also the possibility of spontaneous Hall effects in collinear antiferromagnets. Now, the trick how to generate a Hall effect in these systems, or allow for Hall effect in these systems, in other words, how to break the PT symmetry, is to introduce additional atoms in the lattice and then place them in a position which is off this inversion center. So these atoms could be simple non-magnetic atoms, and if you place them in a non-centrosymmetric position, you will break this PT symmetry. You cannot do anymore an operation of spin, flip, and then inverse space inversion to recover the original state because of these additional atoms here. So if you have a crystal which has this type of broken symmetry, and there is an example of ruthenium dioxide, which is a member of a very broad family of collinear ruthyl antiferromagnets, this in principle allows for the anomalous Hall effect. Now, this is not only a theoretical prediction, but it's also been experimentally verified recently in this ruthenium dioxide that you can have the anomalous Hall effect. Again, the size of the effects is comparable to all of these simple film magnetoresistance signals of the order of 1%, which means compared to anomalous Hall effect in other systems, including ferromagnets, is large, but remains on the order of 1%. Also, these collinear antiferromagnets can host the topological wire-like features in the electronic structure, but one again needs to find the ideal material system where these would lead to the singular behavior of the anomalous Hall effect. Now here, I remarked that there's plenty of collinear antiferromagnets that can in principle host the spontaneous Hall effect. In fact, 10% of all known magnetic structures reported in one of these famous databases, the Bilbao Magnedata, 10% of the structures are collinear antiferromagnets which can host the Hall effect. Well, another remark that I like to make is that these collinear antiferromagnets which host the spontaneous Hall effect, they have a very peculiar type of spin splitting, which is nothing like the spin splitting we're familiar with from a spin orbit coupled system or ferromagnetic system. So you can have this large spin splitting even if you turn off spin orbit coupling and the spin splitting, which gives you a zero net moment, as you see. So this is a new type of spin splitting in electronic structure, which besides the anomalous Hall effect can also lead to many other phenomena yet to be identified and explored. So let me close the first chapter of this talk about readout of the antiferromagnetic state. And now let me move on to the next chapter, which is going to be on writing. And of course, historically, when we talk about writing information into magnets, we talk about magneto recording. That means manipulating or switching the magnetic state by external magnetic fields. This is something that is still done in hard drives. And writing the state or manipulating the magnetic state by a magnetic field is something that made people think that antiferromagnets are really useless for applications. Because if you wanted to transfer the same principle of using magnetic fields to reorient the moments to antiferromagnets, in a straightforward way, you would have to wind coils around each individual magnetic atom and have to do it in a way that one coil generates magnetic field in one direction and the neighboring coil in the opposite direction. So that seemed, and I think still seems infeasible, but fortunately we live in the era of spintronics, where we have devices which use other means of recording or manipulating the moments and magnetic field, and that's spin currents. And so one of the phenomenon that is used in commercial magnetic random access memories is the spin transfer torque, when from the reference magnets we inject spin angular momentum into the recording magnet and transfer the spin angular momentum, and this causes switching of the magnetization in the recording magnet. And the fantastic feature of this effect is that we can control the switching by just changing the polarity of the current. We live now in the 21st century, where we have discovered an alternative means how to switch magnets. It started from recognizing that even by taking a non-magnetic material, we can generate non-equilibrium spin polarizations just due to the relativistic spin-orbit coupling, and we will get spin accumulation wherever or whenever there is inversion symmetry breaking. Now, if we combine this effect with a magnetic order in equilibrium, so if we get these non-equilibrium spins in contact with a magnet, a ferromagnet in this case, we can also induce current-induced switching. And because it's relativistic in origin, the phenomenon is called spin-orbit torque, and it's now also in the research and development phase for the new generations of magnetic random access memories. And it also allows for controlling the switching by the polarity of the electrical current. Now, to adapt or modify this effect for antiferromagnets, the thing that we need to generate or control is the spin accumulation or non-equilibrium spin polarization, whose direction would flip when we go from one antiferromagnetic sublattice to the neighboring antiferromagnetic sublattice. And this can be achieved in systems where instead of having a global inversion asymmetry, we have a local inversion asymmetry at these magnetic atoms lattice sites. So these two sites are inversion asymmetric positions of atoms, and the breaking of the inversion symmetry has an opposite sense. This is another way of saying, in fact, that this crystal has the combined PT symmetry. So the very same PT symmetry that allowed us to have in principle the Dirac points now also allows us to electrically control the direction of the antiferromagnetic moments, which in the ideal world would allow us to control the opening and closing of the gap of the Dirac point, for example. So we have in crystals with this symmetry, and copper manganese arsenide is not the only example known. We have also manganese to gold, which is the same symmetry properties, where we can electrically generate non-equilibrium spin polarizations, which are commensurate with the staggered magnetic order, and can therefore manipulate it as efficiently as the spin-orbit torque in ferromagnets. Now again, I emphasize that this is a bulk effect that happens in simple antiferromagnetic films. In parallel, there are lots of studies where people are exploring instead interfaces, could be, for example, non-magnetic and typically insulated antiferromagnetic bilayers, or ferromagnet antiferromagnetic bilayers. So these are, there's a lot of research of these systems as well, but as I said from the beginning, I will focus on phenomena that happen in bulk of these films and not at interfaces. So let me just continue in this spirit. So I'm showing again the images that I showed already before in the chapter on readout, but now I'm combining writing and readout. So because of this spin orbit torque switching, we're able to reorient large macroscopic domains in copper manganese arsenide by 90 degrees, image it by this X-ray magnetic linear diachroism, or also detected electrically by an isotropic magnetoresistance. Now, let me emphasize at this point that it is indeed very important when we study antiferromagnetic devices not to rely only on electrical detection, but to have a detailed image of what's going on with the antiferromagnetic order. Because the typical currents are relatively high that we applied, similar to ferromagnetic spintronics. So there could be structural artifacts that contribute or would contribute to the electrical signal. So having magnetic images is very important. Now here, the X-ray imaging is particularly useful because you can, for example, compare the magnetic linear diachroism with magnetic circular diachroism. In copper manganese arsenide, the magnetic circular diachroism, which is the analog of Hall effect, should not exist. So if there was any magnetic circular diachroism signal, it would be due to some unintentional ferromagnetic inclusions or impurities in the system. But in these experiments, the XMCD signal is 0. So this makes it clear that the signal originates from antiferromagnetic order. In X-rays, we can also switch from manganese edge to copper edge, for example, and see if the signal that we're detecting is indeed of magnetic origin. If we saw the same signal at copper edge, we would understand that the changes are because of some structural modifications. But in this experiment, it's been verified that there is no signal on the copper edge, which again confirms that the signal is because of magnetic origin and specifically of antiferromagnetic origin. And other important confirmation experiments are trying to reorient your antiferromagnetic moments by large magnetic fields. So this is, and again, example in copper manganese arsenide, where you can have spin flop reorientation at between 2 and 4 Tesla. And you see a resistivity change, which is comparable to what is seen in these electrical switching experiments. So we can now electrically switch and also electrically detect the reorientation of the magnetic order. So the next very natural steps in experiments were to test whether we can scale the pulse length beyond the length that has been achieved in ferromagnets. In ferromagnets, with spin orbit torque, people managed to switch systems with pulses below 1 nanosecond. But the problem is that if you go below nanosecond, that means above gigahertz, then suddenly the energy required for switching starts to increase with decreasing the pulse length. This is an experimental image here, which shows the energy required to switch an antiferromagnet, again, the copper manganese arsenide, as a function of the inverse pulse length. And what you see is that in antiferromagnet, you can in fact extend the operation of your device all the way to the terahertz pulses. That means electrical currents, pulses of the length of 1 picosecond. So it seems that one of the expected advantages of antiferromagnets compared to ferromagnets, that means their speed could indeed be realized in these devices. Of course, then the question is, what is the ultimate speed, or what is the minimum pulse length that you can use to switch such an antiferromagnetic device? But if we go beyond the terahertz, if we go beyond 1 picosecond, we actually are not anymore in the regime of generating spin orbit torques by electrical currents, but we enter the field of optical switching. And traditionally, in ferromagnets or ferrimagnets, systems with a net magnetic moment, ultra-fast switching by single femtosecond pulse has been a field completely separated from the electrical switching by spin torque mechanisms. And as of recently, when we look at this recent review article on all optical ultra-fast switching in magnets, it's been realized that there's only one mechanism that allows for switching by ultra-short single femtosecond pulse, and the mechanism works in ferrimagnets. It's very important to have two sublattices with different size of the magnetic moments and also different number of these moments present in the lattice. So let's quickly go through the basics of this mechanism. It's based on the conservation of angular momentum. So imagine that you start with this perfectly ferrimagnetic antiparallel phase of these large moments being gadolinium and the smaller moments being iron. Now, when you excite the system with a strong femtosecond laser pulse, you start demagnetizing the system, which means in principle that you start flipping the spins. But if you want to conserve the total angular momentum, so flipping one gadolinium spin would then correspond to flipping approximately 4 iron spins, and the total angular momentum is conserved. When you go to the next step of the demagnetization, you flip the next spin, gadolinium spin, and you flip next 4 small spins, iron spins. But what you see here already on this cartoon is that you create a transient state which is not anymore antiferromagnetically coupled, but is ferromagnetically coupled. And indeed, this is something that has been observed in an experiment, that at this transient state, you already reversed the moment of the iron sublattice. When you continue, you flip the third moment of gadolinium, you again flip next 4 iron moments. And what you get in this case is demagnetized gadolinium and already reversed iron sublattice. And once you then flip the next moment of gadolinium, you see that you complete the reversal. So this is a mechanism which works, for example, in this gadolinium iron compound here, but it clearly requires 2 different sublattices of a ferromagnet, so it seems to exclude antiferromagnets. So that brings me to the, let's say, wrap up of what we've learned so far about the reorientation type of switching of antiferromagnetic systems based on these simple single layer film antiferromagnets. We can do this, we can explore, we can also explore some intriguing topological variants of these phenomena and features. But we also saw that we inherited some weaknesses from the ferromagnetic spintronics principles that we adapted to antiferromagnets. And one of the weaknesses was that we see these low resistivity readout signals in simple magnetic films, and also that there is no obvious extension of the current-induced spin torque mechanisms of switching towards the ultra-fast optical switching by the single femtosecond laser pulses. So in the remaining part of the talk, let me just give you a brief flavor of a new type of switching mechanism that we discovered very recently, which is fundamentally distinct from what I've talked about so far. It's a completely different switching principle. So just to compare the standard, the conventional reorientation switching principle with the new one, which I will call from now on quench switching of antiferromagnets. So in the reorientation switching, we saw these large domains, and by applying current pulses, and I'm now more specific, starting from about 5 × 10⁶ amps per centimeter square at these pulse length, we could switch these large domains. That means reorient the nail vector by 90 degrees. Now, when we take the very same device, the very same single layer film copper manganese arsenide, and we apply about a factor of 2 larger current pulses than are the minimum pulses for the reorientation switching, we see a completely different picture in the X-ray magnetic linear diaphragm microscopy. Instead of seeing reorientation of large domains, we see that we broke our system into this nano-fragmented domain state. We saw it not only in this synchrotron X-ray magnetic linear diaprism studies, but also in the magneto-ZBAC laser imaging in the lab, which I already introduced earlier in the talk, and also by another study, which is the nitrogen vacancy diamond magnetometry. Also in these experiments, we see that starting with large domains and applying these slightly larger pulses than the ones that we normally use for the reorientation switching, we shatter the large domains into these small nano-fragmented states. Now in these laboratory experiments, we can then wait days or even week, and we can then re-image the system. And what we see is that the system tends to reconstruct after some time these large domain state, which then is the equilibrium state. So the nano-fragmented domain state is metastable. However, we can deliver these short pulses, and these nano-fragmented states remain in this metastable configuration for macroscopic timescales. So this is the microscopy image. Now let's take a look what type of electrical response we get in this new quench switching regime. So when we talked about the conventional reorientation switching, whether it was in ferromagnets or antiferromagnets, we could control it reversibly by changing the direction or the polarity of the writing current. In the quench switching experiment, we will keep the switching is in fact polarity independent. It doesn't depend on the direction of the electrical current, but we can control the switching in a reversible manner by changing the amplitude of the current pulse. So if we deliver a stronger pulse, we have this higher resistivity state. And then if we deliver a weaker electrical pulse, we switch the system into a lower resistivity state. So we can reversibly and reproducibly switch the system between high and low resistivity state by changing the amplitude of the writing pulse. Now, what is striking is that these resistivity changes, again, in a simple single layer antiferromagnetic film and in a device which is just the simplest 2-point, or if you want, a 4-point resistivity measurement device. We see relative changes at room temperature, which reach 20%, and at low temperature changes reaching 100%. So we can quench our system into a resistivity state, which is which has resistivity twice as large as the residual resistivity of the film in the large domain state. So this seems to be one way how to get around one of the problems of working with thin films, and that's the small readout signals. Here we see that we can have readout signals of the GMR or even reaching the TMR amplitudes. What is equally promising to us is that we can also now use the same switching mechanism, not only for electrical switching, but also for optical switching. So here is an example of delivering laser pulses. When we deliver a higher intensity laser pulses, we switch the system into the high resistivity state. And when we deliver a weaker intensity by defocusing the laser, we can switch the system into a lower resistivity state. And this switching can be done even with a single 100 femtosecond laser pulse. And so we have now ultra-fast switching in terms of the pulse length, where we can go all the way from DC to a single femtosecond laser pulse. And when we look at the energy densities required for switching, they are comparable for the nanoseconds, picoseconds, and femtoseconds. So indeed, we can extend switching from all the way from nanoseconds to femtoseconds without delivering excessive amounts of energy. I'd like to also point out that the energies that are required, the laser energies that are required to achieve this single pulse switching are comparable or even lower than what's been used in these single pulse switching of the ferrimagnets like the gadolinium iron. I've already mentioned the metastability of the retention, if you want, or of the stored information in these devices. So indeed, if we switch the device by the short pulse, which can be as short as a femtosecond laser pulse, or it can be a microsecond or millisecond pulse, and then follow the readout signal, we see that there is this smooth relaxation of the signal. Now, the typical retention or relaxation time that we observe is exponentially dependent on temperature. So our signal that we see here would relax on time scales of seconds or tens of seconds at room temperature. If we cool the system down to 200 Kelvin, it becomes a time scale of years. And of course, if we heat the system up, we will accelerate the relaxation. And this is, by the way, also the mechanism which allows us to quickly erase the state and write a lower resistivity state, is because we highly accelerate the relaxation by delivering the second pulse, and then we just write the lower resistivity state. So what we get from this is that we see that the signal that we can write in these devices depends not only on the amplitude of the pulse, but it also can depend on the order of pulses. So if we first deliver the stronger pulse and then the weaker pulse, we have this falling edge, but in the reverse order, we have this rising edge. And we can also measure the delay between pulses, because the falling edge, what you see here, depends on the relative delay between the first and second pulse. So in this single quantity of this falling edge, we can code the order and the delay between pulses, which, by the way, is one of the functionalities which is needed for developing spiking neural networks, in particular for setting up the synaptic strength. In the same neural networks, when you want to have the leaky sum function of your neuron, here the neuron potential depends not only on the number of pulses, but also on the delay between pulses, and that's exactly the same, the functionality that we can also realize in our devices. So this opens to us another completely new research areas from, let's say, the digital memory devices towards the analog neuromorphic devices. And it also tells us that maybe we can play many more games and tricks in our labs, but it is also worthwhile starting to think of potential applications of spintronics. And this is the last slide I'd like to show, more for entertainment than serious slide. The serious part here is only that I'd like to emphasize that it's worthwhile to transfer what we do in our labs into some development electronic boards, not as a final commercial applications, but as a first step from the research towards application. So here's an example where we packed all the measurement equipment from the lab into this very simple analog printed circuit board with the antiferromagnetic device. And here you see what we measured in the lab on the same device, the falling edge. And here is the same response, but now detected using this very simple analog circuit board. And just to demonstrate that this board can work in ambient conditions, we can just deliver two pulses, one stronger, one weaker, from two sensors, which sense a moving vehicle. And we will see in the last slide here that if the vehicle is moving in one direction, and this is, by the way, taken in one of our real IoT development sites. So first sensor sense the stronger pulse, second sensor sense the weaker pulse, and we record on this simple board falling edge. If now the vehicle is entering the garage, here is moving in the opposite direction, we first hit the sensor sending the weaker pulse, then the sensor sending the stronger pulse, and we have the rising edge, and that tells us that there's an opposite direction of the vehicle. So that to think that this is a new commercial device, and then we have the first commercial applications of antiferromagnetic spintronics. This just shows the idea of now moving from laboratory research alone also towards these development boards. So my time is up. Actually, I am more than up, 50 minutes. So thank you all very much for joining in, and I'm looking forward to your questions, and obviously looking forward to the next talk next week. Thank you.
Thank you, Thomas. Unfortunately, I'm not sure if you guys can do the clapping or can do the clapping. It's unlikely that it works in here. On the other hand, this was a magnificent talk, as I expected. And maybe now we can address some of the answers. I know some of you, we've been asking some questions during the talk. Some of them we try to address, some of them not. I'm going to now, to some of you, allow to talk, to speak, so you can unmute yourself. I don't know, maybe Igor, Martin, maybe you can unmute yourself, and you may be able to speak if you want to ask your question regarding ruthenium.
Oh,
ruthenium, yeah. Go ahead.
Yeah, I mean, that's probably a bit of side issue, but you mentioned
so this is Igor Maslin, huh?
Hi, everybody. Nobody can see me. Yeah, that's a bit of side issue, but when you mentioned that you can switch optically only if ferromagnetism is involved. But on the other hand, I think it's known experimentally that iron rhodium can be switched between antiferromagnet, clean antiferromagnet, and ferromagnetism optically with optical pulses. Can you comment on that?
Right, but in iron rhodium, the ferromagnetic phase is stable at high temperatures, about 100 degrees above room temperature, and then the antiferromagnetic phase is stable at lower temperature.
Right, but it can be at the same temperature optically also.
Yeah. Sorry?
It can also be switched optically at the same temperature, without at the time scale, which is not really compatible with lattice expansion, lattice heating. I don't know if it's fully understood yet or not, but I think it was demonstrated experimentally that in this pump probe experiment.
Okay.
So let's. So thanks for the comment. There's another question by Shamuk Kara. Samathan, I've promoted you now that you can talk if you like to unmute yourself. I'll give you ask your question, or maybe I can ask the question.
Thank you.
Thank you for an explanation. More of magnetospheric.
Okay.
I would like to know.
So let me mute you because I think it's difficult to hear you, but I can actually, maybe you can read the question. Sorry. The question is, may I know more about the mechanism of magneto-Seebeck effect by laser heating? Do you have any comment on that?
Sure. Yeah, so again, as I said, the thermoelectric magneto-Seebeck effect is the direct analogy of anisotropic magnetoresistance of the electrical magnetoresistance. So in anisotropic magnetoresistance, what you do, you apply electrical bias, and what you measure is the current in response to this, electrical current. In the Seebeck effect, instead of applying electrical bias, you apply the temperature gradient, for example, by laser heating your system. And in the response to this, you can measure some electrical current or electrical voltage in an open circuit. So what happens is when you shine the focused laser spot, it will generate a heat gradient around this laser spot. And if in this case you have portions of your material which have different Seebeck coefficient, for example, when you're close to a domain wall between the two different directions of the nail vector, the two domains would have different magneto-Seebeck effect. and therefore you will generate a net electrical readout signal. And so this is the way how you can image, for example, the domains or the domain walls in particular in these antiferromagnets.
Okay, let's hang on. There's some more questions popping up. Let's see. Oh, Andy just showed up. That's wonderful. Let me actually find Andy. Yeah. Okay. So Andy, now you are unmuted. Maybe you can ask your question, Andy.
Oh, yes. Thank you. Can you hear me?
Yes, now we can hear you.
Okay. Very, very nice talk this morning. And thanks for organizing this. My question relates to your last topic, this intriguing quench switching, and whether you have an idea of the mechanism there. You said it's a different mechanism from the spin orbit related effects, but I don't think you discussed what it was.
Well, we have images of what's happening. So when we are in our reorientation switching, what we see in X-ray magnetic linear diaphorism is actually switching of these large domains. So it's the same material. You start with a pristine material, and then you start pulsing it, but gently with weaker pulses. And then you see switching by 90 degrees of these several micron size domains. And you can control the switching, for example, by polarity of the pulse. So it has all the features that you expect from the spin orbit torque. Now, when I go to the, I use the same material, same film, but instead of applying weaker pulses, I'm applying slightly larger pulses. And in fact, sometimes it's very difficult to find the regime where you have this crossover because it's very, very close by. So instead then of reorienting your large domains, what happens is that you shatter the large domains into this nano-fragmented domain state. And in response to this, you will see a large increase of the resistivity of your film, which is 2 to 3 orders of magnitude larger than what you see in the reorientation switching.
Okay.
Okay.
So I think Jesus Carlos Toscano Figueroa has a question that I think is quick to answer regarding the measurement part. Jesus, do you want to ask your question?
Yes, hello, can you hear me?
Yeah.
Okay, thanks for the talk, very interesting. This particular slide is where my question comes from. So if I understood correctly, you're modulating your laser very fast, right? The amplitude of it. And the response that I can see on your upper and lower plots in here is of the order of seconds or so. My very perhaps very naive question is, why is this discrepancy between the time range in which you are controlling your laser and very orders of magnitude different the response that you're getting, at least electrically, in the delta of resistances?
No, so in the laser experiment is the same as in the electrical experiment. So basically you deliver the first pulse, which is short. In electrical experiment, we did microsecond pulses, but nanosecond pulses. And then you wait a macroscopic time. So you wait seconds before you deliver the next pulse, okay? So this is the electrical experiment, and the optical experiment is exactly the same spirit. You deliver the optical pulse, which we did either train of pulses to see how it depends on the number of optical pulses, or we could do a single femtosecond laser pulse, deliver it, and then wait for a macroscopic time, second, then deliver the next pulse, which has a lower intensity. And we can do this by just slightly defocusing the same level.
Sorry, there's some meeting going on that I probably need to.
Well, people should mute their
Try
microphone.
to mute yourself only when you're asking a question, please. Go ahead, sorry, Thomas.
Yeah, well, I think I'm kind of
Done with the
question. I don't know if I.
So Tero, I believe you have a question.
Yes, hello. Tero Heikkilä, thanks for the nice talk. I actually had two questions. The one which is related here. So I could maybe ask both of them, and then you can choose which one to answer. But so the question actually is related to what actually is the mechanism that creates this long time scale. Is it related with the magnetization switching, and that's why it's very, very long? And then actually the second question is about the spin splitting. You mentioned in one of the slides that the effects related with the spin splitting in antiferromagnets compared to ferromagnets are quite interesting. And I was intrigued by this, so maybe you can develop a bit on those.
Right. So quickly remind me, the first question was about, yes, about the relaxation. So we think that this type of switching is quite unique. We could not find any counterpart in the ferromagnetic literature. And so for some reason, we get stability or long-term metastability, if you want, of these very small domains. We can, from the microscopy measurements, we can infer that these features are on the scale of 10 nanometers or maybe even smaller. Now the question is what keeps these features stable or metastable for macroscopic timescales. And here, I think very important feature of antiferromagnets is the lack of long-range interactions. So as long as the features are very small and you have you have quite efficient short-term exchange coupling interaction, and that will force the domains to expand and move towards the equilibrium state. However, once you get to sizes which are sort of beyond the reach of the short-range interactions, and you do not have the long-range interactions that would drive the system towards the large domain equilibrium state, the relaxation will slow down, maybe also because of some pinning on defects. That's also a possibility which can play a role here. But certainly very quickly, the relaxation process towards the large domains is slowed down, and in all the way such that we can observe it at macroscopic timescales. And I think the critical feature here is that we do not have long-range dipolar coupling in antiferromagnets. But we don't understand all the microscopic details, and that's obviously something which is one of the key things that we want to explore now. Yeah.
So it's a bit like a glass in this case.
Well, we cannot say decisively what exactly is the structure of these things because it's below the resolution of the techniques. And that's why, for example, we're now moving to imaging techniques with atomistic resolution, like, for example, Lorentz transmission electron microscopy, where we have some preliminary results of very sharp domains in antiferromagnets, but that's something which is still, we still need to work and do a lot of confirmation experiments. Okay?
Okay, so then the next one is idea. Sorry. This is
Cairo, can you hear me?
Yes, I can hear you.
There was a second question I was supposed to answer about the splitting of the bands, if you allow me.
Sure, sure, absolutely. Yeah, please.
So this indeed is very unique. It's been recognized by our student Libor Schmeichel, but he's not a PhD student anymore, but also by other groups like the group of Alex Junger, is this peculiar spin splitting, because what you have here is a large spin splitting, but in systems which have zero net moment, but also no spin orbit coupling. So you can have, let's say, spintronic phenomena due to large spin splitting in the band structure, while still spin is a good quantum number. So that is the thing that we think is quite intriguing and could lead to some spin transport, long distance spin transport or spin coherence phenomena, but this is something which is yet to be explored.
So then the next question was from Adiam V.
Yeah, can I ask? Can I go? Hello?
Yes, go ahead, please.
Yeah, so it's exactly on the same slide what is been running now. So if I have an antiferromagnetic like Fe2O3, which is having collinear antiferromagnetic structure, above the Morin transition, So since it's also a semiconductor, so you will also win in the case of resistance change, also maybe higher. So that material also, would you expect show this spontaneous Hall effect?
So you would have to, I would have to see what is the symmetry of this specific material, whether it allows for the Hall effect. Basically, what you have to check is that the material is in the magnetic point group, which is one of the 31 ferromagnetic point groups. When we talk about these ferromagnetic point groups, it doesn't necessarily mean that the system is a ferromagnet. It just is in a symmetry group, which in principle allows for the net moment. So this ruthenium dioxide is crystallizes in one of these 31 ferromagnetic point groups, but still it has a vanishing. This is something that
so do you mean to say that it's a centrosymmetric and non-centrosymmetric?
It could be both centrosymmetric and non-centrosymmetric. That both can in principle have an almost Hall effect. So, yeah. So for example, this ruthenium dioxide is centrosymmetric. It still has a central symmetry. It does not have the combined PT symmetry, but it still has symmetry. There are other examples where you can...
listening to your talk and explaining, understanding the ruthenium dioxide, since I work on oxides, maybe I know a bit of them. So I would expect even Fe2O3 also should show, since it's being a semiconductor, your rho H by rho value is 1%. There I would expect it to be slightly higher. It will be reasonably higher.
Yeah, that's a very good point. We think that for many of these effects in the singularity films, including the quench switching I talked towards the end, the way to go is to go towards more resistive materials like semiconductors, for example. It's reminiscent of the literature on phase change memories, right? You get large changes in resistivity in materials which are just at the border between metallic and insulating.
Okay, thank you. I have one more question. Can I go ahead?
Hey, actually, let's allow, because I think there's a few other people that want to ask questions. Maybe if there's more time later, we'll ask us to continue. But let me ask because there's a few people that I have their hands up, so I'm going to allow them to see if they want to ask their questions first. I think I just promoted them to talk. The ones that had their hand up, do you have a question or not? Don't know which ones. Xiang Se Chen.
Yeah.
Go ahead.
Hello, Professor. I'm Xianzhe from Tsinghua University. Thanks for your nice talk. I just have a little question. You mentioned the anomalous Hall effects could evolve in the collinear antiferromagnets with PT symmetry broken. So I wonder whether the magnetic spin Hall effect could also evolve in this system.
Yes. The answer is yes.
Okay. Thanks, sir.
You're welcome. And then maybe there's another question from Sergey Shian 123. I don't know if you would like to ask a question. You had your hand up. Okay, maybe not. So we have another question from let me actually promote Vahum here. There's one more. So Vahum, you're now promoted. If you can maybe ask your question. Yeah.
Perfect. Hi, thank you very much. Thanks for such a good talk. From what I could understand, again, I had a simple question really. In terms of using, whenever you use, for example, optical switching, you're using light. So I'm wondering, is it an effect, what you observe, for example, the change in the reflectivity, is it polarization dependent somehow, if it's a circularly polarized light versus linearly polarized light? Does that play a role at all? Would you see any change, for example?
So you're referring to this optical switching experiment?
That's right, yes, the one in which you use optical switching.
In this, it's kind of slow moving, sorry. Yes. So you actually mentioned something I did not mention, is that indeed you can also detect the switching not only by measuring the resistivity electrically, but also you can detect it optically by measuring reflectivity of the material changes, which to us is extremely important because now we have the tool to try to do time-resolved experiments and really observe the dynamics of the switching. And this is obviously the next on our to-do list, is to use this reflectivity and to do the time resolved measurements.
Sure.
In terms of switching, we tested that it's polarization independent, as emphasized here on the slide. It doesn't depend on the polarization, whether it's linear along different planes or whether it's circularly polarized. So it's a polarization independent in analogy to the polarity independent electrical switching.
Okay, great, cool, thank you.
Okay, thank you. So let's mute again. And then this, I think one person that may have, are we done with the questions? Oh no, Inan, hang on for me. So Inan, can you unmute yourself?
Hi.
Hi, good to hear you.
From Istanbul. I have a question, Thomas. I have a question regarding the comparison of the antiferromagnets and the ferromagnets regarding the Dirac point. Did I catch you right that you said that there is no, Dirac wild points when you have a ferromagnet, or I just confused with that remark actually.
Okay, so what I call Dirac point is a point where I have a crossing of two doubly degenerate bands. So I have Kramer's spin degeneracy and I have a four-fold degenerate crossing point. Let me call this Dirac point. When I have splitting of this into the two wild points, I have basically two crossings which are doubly degenerate, so it's a crossing of a singly degenerate band. So this thing is allowed in ferromagnets, the wild points, but the Dirac point is not allowed in ferromagnets because you cannot have a ferromagnet which has the PT symmetry.
Great, crystal clear. So I just didn't realize that because I was just confused that you would have wild points, obviously, with a ferromagnet.
Yeah.
But I see that you're talking about a Dirac point, which is doubly degenerate, basically two wild points, exactly the same point, right?
Yeah.
Okay, great. Thank you.
Great. So I think we have a few comments from Igor, but those are comments. I think we are at the end. I don't see any more questions. And I would like to join with everybody because, first of all, I would like to say a few words to everybody to come to this. I was not knowing what to expect. The announcement went on Sunday at 11:30 at night. Within 1 hour, there were 250 people sending requests to attend. We were today 800 people attending, 500 here in Zoom, 300 through YouTube. And maybe there's room there to expand to 1,000 participants if this continues like this. Of course, the big attraction was Tomas giving these wonderful reviews and having given many wonderful plenary talks already on the subject. And I really thank you, Tomas, for doing this, and from all of us, since you cannot hear the clapping of everybody, I think the clapping from everybody is unanimous. Everybody can raise their hands, I guess, to clap in this case. And thank you once again to everybody. And I think with this, I will end the meeting. And everybody's clapping. You can see that maybe on the side. I don't know if you can see this, but everybody seems to join on the clapping, the ones that are starting here. So yeah, I think every single one of you. Thank you very, very much. That's the hands up. That means that there's no questions. just the hands up. And as I mentioned, the next week is Carlo Benacker, a fantastic speaker as well. Just equal, I'm not sure if as good as Thomas, but definitely on a fantastic different topic. And please advertise it. Please give me feedback. I'm happy to hear feedback of how this went. If this was well done, any ideas of how to improve it, of course, is always welcome. In my case, I found myself very busy answering questions, so I couldn't follow the talk, so I will have to watch it afterwards. Also, if anybody that you hear that had a trouble logging into Zoom, to let me know, and maybe in order to increase from, we have a 500 attendees that we can have, but we can increase it obviously to 1,000 or more if there's a need and a call for it. And with that, I thank you all for coming at this time, at this crazy time, and maybe we can use this opportunity to create a new type of interactions where there's more people that can attend and not having to travel. And with that, I don't know if Thomas, you want to say a few words?
Well, I definitely want to say thanks, Cairo, and your crew for setting this up. It's been perfect. It didn't work yesterday. It worked perfect today. So great job. Thanks a lot.
Okay, so thank you all. And with that, I will stop the recording and stop the